All right, and recording is rolling. So got another Friday. Oh, but you guys just turn in your AP Physics Review 1 quiz. Remember that looks like review quiz number 1. Looks like this. Mostly kinematic related questions. Three crossover questions. So if you guys are looking for what's coming up next, I'm working on you guys' next review quiz. I want to give you guys these review quizzes, of course, leading up to the actual exam. But another thing that's come up is AP Classroom Unit 3, Multiple Choice Part B. I'm thinking probably a few Wednesdays from now, Wednesday, February 23rd is probably a good day for that. That's after this upcoming 4-day weekend, which is not this coming weekend, but the one after. So you got some time that you want to start looking at those. You guys remember Unit 3 was both centripetal force, like mv squared over r type stuff, and also universal gravitation, because you can put those together and get like orbits, that sort of thing. Okay. Today, did you guys get? I passed these around. Did anybody not get one of these? Oh, okay. Great. Can you pass a couple of these back? Okay. In case if you need one, raise your hand. Get back to you. Right before we hit that, because I want to explain the story, set you guys up with that. Let's do a poll. Where's my poll paper? Here it is. All right. So next week, what I'm doing with my honors kids is I'm taking the whole week to do some SAT math, because that's the part of the SAT I can help out on. And thinking, well, what should I do with AP students? So I can come up with 3 options, and I'm going to poll you guys. Right, so option 1 is that we can not do any SAT at all and just do all AP stuff. So like all FRQs and AP questions. Okay? Or I could do like a short form with you guys, maybe take a couple of days to do AP stuff and a couple of days to do SAT. Or I could do what you guys want to do with my honors classes, which is take the whole week and do SAT math. So I want to see show of hands what you guys are think between those options. You know what? Give you guys a couple of minutes to think about that. So just want to think about some things, but come back and I'll poll you guys and we'll see about that. All right, so let's take a look at this speed of light puzzle. Now this one, I think I took you guys through the story very quickly yesterday, so let's do this a little bit slower. Think about how this works. Oh, yeah. Oh, Nico. Yeah, go ahead. Yeah, so the speed of light was calculated accurately back in 1849. This guy did this with a toothed wheel and a mirror. Now, what he did, find one that has some drawings on it. Okay. He had some light source representing with a candle that, okay, well, one of the light rays, say, would have gone in a straight line to this mirror that was several kilometers in the distance, maybe 3, 4, 5 kilometers back, like that. And then the ray would bounce back, and here's an eyeball to represent an observer. Okay, so you can observe the reflection of the light. Okay, so that's all fine and good. Okay. But what if you give this tooth wheel a spin? Right now, because light has a finite speed, if you spin this fast enough, then you would actually observe something different. And I'll take you guys through why. Okay, so say a light ray goes through a gap between the teeth. I'll call that a window. So we got some teeth and we got some windows. An equal number of teeth and windows, right? That'll come back later. Okay. So light ray goes through a window, reflects off this mirror, comes back. And if this wheel is spinning fast enough, then is it possible that by the time the light ray gets back, one of these teeth will have covered a window adjacent to it, right? If he just turns a few degrees. And then what would the observer see? Well, wouldn't that light ray have been blocked? And any light rays that would have been hitting teeth never would have gone through in the first place. And light rays going through these windows would have come back and hit a tooth now that it's turned and there's a tooth in the way. So yeah, this guy would not see a reflection of the light at all. Okay? And maybe a little side detail to connect some dots here. What about if the wheel starts from rest and it speeds up? Say it has some angular acceleration. So it's going, what would that process look like? Well, it would start out that you could see the reflection, and then it would look like there was a door that was closing on the reflection of that flame until you really reach the correct angular velocity where it exactly blocks it completely and you don't see the reflection at all. Right? Now, if you know the number of teeth on the wheel, the distance to the mirror, and how fast it's spinning, there is enough information lying around there that you can calculate the speed of light. Or well, that's what Hippolyte Fizeau did back in 1849. Now, let's zoom back to modern day. So we are in the future, and you guys know what the speed of light is. It's 3 times 10 to the 8 meters per second. Or if you like, it's more precisely this number, 299,792,458 meters per second. That's a definition of the speed of light. So actually, a lot of our base values in the metric system, scientists are trying to base them all on fundamental constants of the universe. I think they've actually completed that now, just in the last few years. Mass was like the last one. But for example, the definition of a meter now is the speed of light multiplied by a tiny fraction of a second. So, you know the speed of light. So your quest is to, you're going to hop in a time machine, go back to 1849, and tell this guy, based on these specifications, the distance to the mirror, the size of the wheel, the number of teeth on the wheel, how fast he has to spin this wheel so that everything comes together and you could do the correct calculation. Okay, so the problem that you're solving is backwards what he was solving. He knew the spin rate because he measured that, and he calculated the speed of light based on that. You guys know the speed of light, so you're going to figure out how fast does the wheel have to spin. Okay, guys get that? Right. So again, I told you the distance to the mirror, the diameter of the wheel, and the number of teeth on the wheel. I'll tell you guys what. Out of these values, there's actually one value you technically don't need to solve the problem. It ends up canceling out. So like if you change the value, it doesn't actually change the answer. Okay. Now, you can solve this whole problem with just kinematic information, right? Now there's linear kinematic and there's also angular kinematic. Do you guys see that poster up there on the wall? It says, it's one with the circle. It says X equals theta R, V equals omega times R. Okay, so that's a translation back and forth between linear and angular motion, right? That might be a really helpful poster today. If you answer these questions one by one, they lead straight to the answer. Now, at this point in the class, what I'm really tempted to do is just take you guys through the whole story piece by piece and solve along with you guys, but today's not going to be that kind of day. Today's going to be an independent working kind of day. So you guys got the rest of the class period to either work by yourselves or with your friends. So if you want to make a team, you can do that and figure out how fast does this guy spin this wheel. Keep in mind, you guys have different numbers. You guys have different wheels. Also, if you have any questions about registration or if you need me to sign any papers about AP classes, then let me know. All right, you guys got the rest of the class.